Well, let's continue on in chapter. Should have got my 3D paint program loaded. There we go. Last time we were talking about algebraic simplifications here. And I think I was having trouble finding the exact reasons behind number 5. Um, okay. Now, the next thing we're going to talk about is complements of a function. Complement of a function f is f prime. And it's obtained from the interchange of zeros and ones for zeros. So very simple when you talk about inverting the value. Complement of function may be derived algebraically through De Morgan's theorems listed in the table. And let me drop a bookmark here. And we'll go to table 2.1. Actually, doesn't know what I wanted. There's the one I want. Just in case we have referred to them today. There we go. Okay, so now I thought bookmarks are down here, but I'm obviously remembering it incorrectly. Oh well. So they refer to complement of function may be derived algebraically through De Morgan's theorems, listed in 2.1. And that's down here. For two variables, De Morgan's theorem can be extended to 3 or more variables. A 3-variable form of the first De Morgan's theorem is derived as follows. Now here we replace b plus c with an x. You may say, well, how can you do that? I can just take two inputs, 2 variables, and just replace them with another one. Well, if you think about it, b plus c, b or c, that's either going to give you zeros or ones. And so it's really just one output. That's why you can replace it with an x. And then by De Morgan's theorem, the a plus x, you got 2 things with a plus or an or between them, and then the complement. That's this theorem 5a. So you got 2 items, doesn't matter the letter, with a plus between them and an or, and then the prime on there, the inverter, and you rewrite those with multiplication, specifically putting a prime on each one of them. Now, how that's read is this is x or y, or I should say not x or y, because that's what that does, is equal to not x and not y. So remember that prime is a not. Basically, if you got addition in there and prime there, then you put a prime on each one of these and put a and or a multiplication in between. But then going back, we said that the x is equal to b plus c, so you plug b plus c back in. And so you got this setup right here. Now from De Morgan's theorem, just applied to two variables. You got b plus c or b or c, and then prime on there. So you rewrite as multiplication, put a prime on each one of those. And from the associative, you can drop those parentheses, because it doesn't matter if you multiply or and those two together first, or if you do the a and b first. So that shows you can do it for 3. You can actually do it for however many. Notice here I got a plus b plus c plus d all the way up to f. And I rewrite that as a prime, b prime, c prime, d prime, all the way up to f prime. Going the other way, if you have a, b, c all the way up to f, there's ands in between those. So, and then there's a prime on there. Then you can rewrite as addition, putting a prime on each one of those. Again, additions or. Okay, so it says find the complements of these. So let's look at that. F1, I guess, equals x prime y z prime plus x prime y prime z, yeah, z. Okay. And we want to find the invert of that prime. Now remember, if you're got our invert, the not on here, and there's a plus in here, we can rewrite that as multiplication. Now, De Morgan's theorem down here says that you got x or y, x plus y. That's theorem 5a. But here you're saying, well, we got more than that. But remember what this all equates to. If I were to put this in the truth table, it just gives me ones or zeros. This just gives me ones or zeros. So really, we just have two inputs here, which means that I can apply De Morgan's theorem here, 5a. So theorem 5a, and addition becomes multiplication. Now, notice when addition becomes multiplication, we put a prime on each one of those. Then that goes away. So we would have x prime y z prime prime, and then x prime y z and prime. So again, this is like one item. This is like one item. So each of those items carrying down, we put in a prime on them. That is no different than what we did right here. We had one item here, one item here. We put a prime on each one of them. Then this is multiplication in here, and we've got a prime on here. We can rewrite this with plus between them by inverting each one of these. That's seen from theorem 5b. If you got multiplication inside and then the whole thing's prime, you put a prime on each one of them, put a plus or an or between them. Which means this first part becomes, now when I put a prime on each one of them, it goes ahead and flips it. So this becomes x, this becomes y prime, and this becomes z. Now this one, this x prime becomes x, this y becomes y prime, and this z becomes z prime. Now let's check that, see if I did it right. X plus y prime plus z. X plus y prime plus z. That's right. X plus y plus z prime. Okay, they say that should be a y. What does that screw up? Helps if you actually write the problem down right. There should be a y prime there. X prime, y prime, z. Okay, so how does that change it? This is y prime here. And this is still y prime here. And then this gets flipped, and that's y. So x plus y plus z prime. Okay, so that checks. And that's how you'd find the invert of that, the not. Okay, let's look at the other one. F2 is equal to x y prime z prime plus yz. And we want to find the complement. So we'll put all this inside of parentheses. Prime. Okay, now you're sitting there, well, what's inside of parentheses? What is it exactly? Well, the first thing that jumps out at me is I got this times this. Or and, if you want to think of it that way, x and this. I can rewrite this as addition. So that's theorem 5b. So if you got something times something else and then the entire thing inverted, then you can rewrite in this manner. So flip each one of them and put a plus between them. That's theorem 5b. So that's going to be x prime. So that flips, put a plus. And then this is going to be y prime z prime plus y z, and then I flip it. Again, this is one item, this is one item. I put a prime on each one of these. Now the x prime is done there. But here we got two things. Got something here plus something. So we got two things added together and then a prime on this. theorem 5a. So I'm going to rewrite this as, how am I going to rewrite it? Okay, two things added together. I'm going to rewrite them with multiplication and put a prime on each one. So this would be y prime, z prime, prime, and yz prime. So then, now I got two things multiplied together and a prime on the outside set of parentheses. That's this right here, theorem 5a, theorem 5b. Just almost seems like I'm going in circles here. So I flip each one of these and put a plus between them. So it'd be y plus z. But there's multiplication here and still here. And this one would be y prime plus z prime. That doesn't apply because the x's here aren't the same. The first items or last items aren't the same. Now we saw earlier where we just multiplied this together. This is if we were in college algebra. But I'm going to check to see if I'm headed the wrong direction. Y plus z, y prime plus z prime. Okay, now it looks correct down to there. Big question is, although they're done before, why can I say I can do it? Because I won't worry about that. We just saw earlier we could do it. Okay, so I got y, and I think it's multiplication, even though it's really an and. Y prime, y z prime, z y prime, and I'll put in right order, y prime z. Community property allows me to do that. Z prime. Now the y prime, I think there was something that helped us there. Right here, postulate 5b. X and not x gives you 0. I have no reason why you can do that, but we'll just say because. Okay. So these go to 0. And I got y z prime plus y prime z plus 0. Those zeros drop away because of postulate 2a. So that gives us x prime plus y z prime plus y prime z. And then we double check it. We'll call it good. X prime plus yz prime plus y prime. Okay, that's right. Yes, ma'am. Okay, here's another example. It says find the complements of functions f1 and f2 by taking their duals and complementing each literal. So I got x prime, y, z prime plus x prime, y prime, z. Okay, so the dual of that is that this is multiplication and, so you can switch it to addition or ors. This is a plus, so you'd switch that to multiplication, and then this becomes additions. Oops. Like that. And then when you take the complement of it, it just inverts each one of these. So notice this. The x prime becomes x, y becomes y prime, z prime becomes z, and so forth. So this is x plus y prime plus z, and x plus y plus z prime. And double check that. And that'd be our complement. Excuse me. Grab a drink here. Now we do our second example. We had f2 equals x times y prime z prime plus yz. So the dual, this x carries down. This multiplication here becomes addition. And then this carries down. So then we take the complement of that. You notice what happens. The x again becomes x prime. This stays as is, but each item inside here flips to the opposite. So that x prime plus, and then that becomes yz plus y prime z prime. Double check it. X prime plus. Oh, I didn't write dual down correctly. Okay, let's try that again. Hopefully I can take dual that too. I'll wake up here eventually. Okay, so y prime plus z prime and y plus z. Okay, let me double check my dual. Y prime plus z prime, y plus z. Okay. So now I invert it. That becomes x prime. This becomes y plus z. And this becomes y prime plus z prime. Y plus z, y prime plus z prime. Okay, and then that'll be your answer. So just a different way of doing those same two type problems. Draw a logic diagram. So maybe I can remember where I put LogiSim. It looks like we're gonna have X and Y come in. And so X and Y. Okay, so I put them a little bit too close together. Do I need X prime, Y prime? I need X prime, and I also need Y prime. Okay, so I'm gonna need an inverter on here. That's gonna give me X prime. Need an inverter down here. That's gonna give me Y prime. Now the big thing here at the end is there's a plus here. So we need an OR gate. It's gonna be here at the end. In the meantime, I'm going to have an AND gate right here. So my AND gates, I'm going to have one right here. And I'll have one down here. These two AND gates are coming into the OR gate. That's because there's a plus between them here. And those are going to give me my output over here. Okay, so let's take a look at our first AND gate here. That's this NOT X and Y. So I'm going to have NOT X and Y come into it. Here's NOT X. So that's going in there. And we also need Y to come in there. It'll come like that. So here's our NOT X and here's our Y. So that's the first part here. NOT X and Y. This one's X and not Y. So not Y is going to be coming into this one, and I need to have my X come into it. So that's my X coming in there. There's probably a better way of doing that. So it's a little cleaner, but that gives you your logic diagram. Okay, here's the clean way. They have the X and the not X come from the top, and the Y and not Y come from the top. And then just come into the appropriate two AND gates, and then come out to the OR gate. Questions on those yet? Okay, let's take a look at this one. Unfortunately, they're covering something they haven't talked about yet. Okay. When you got this, let me actually do a screenshot of that. First rule of textbooks is you shouldn't cover stuff you haven't, or you shouldn't put stuff in a practice that you haven't covered yet. But they did. Okay, so let's go back. Um, there we go. Okay, first thing they say what Boolean expression is implemented by following logic diagram. This looks like an OR gate, but then it's got this extra line on here. If it looks like an OR gate, like this right here, and you got the extra line on here, this is referred to as an exclusive OR. And we'll talk more about that 2 sections from now. But basically, you take your 2 inputs into it, and you put this symbol in here between it. So you got your plus. Now you can also rewrite it this way, and I'm not sure which way the instructions will do it, but we'll put the plus with the circle around it. So for this one right here, I don't know much about it, but I know right here in the middle is our exclusive OR. So we got a plus here, and then we'll have something here and something here. So going backwards, we have an AND gate here. And unfortunately, they gave this. Kind of takes away the fun of it. But an AND gate, you think of as multiplication on that. So if I were to trace it back, if they hadn't given it to us, I trace it back to here, and this would tell us this is X. This one, if I traced it here, it went up here through an inverter to Y. So this would give us Y prime. So that's why they get X, Y prime. Now what follows that, come down here again, pretending they didn't give that to us. Our first input, come back to here, follow that, goes to an inverter, and then goes to X. That means this is X prime. This one, going back, is this line goes up to Y. So this would be X prime Y. Now let's see what they put. They might not even use that symbol. Okay, so put an inverter on there, but don't really say why. And then they go through some simplification. This is our duality, where this addition becomes multiplication, and you just put a prime on each one of those. Then this comes that. You like FOIL it, and then simplifies to this. Is there anything we've covered to explain why they have put the prime on there? I mean, I can flip ahead. Think about that. No, because we haven't even seen that symbol. How could you know that? So if we had this, oops, up here, we had our XOR here, then you can rewrite it this way. So you put x and then y prime. So for this, let's see, that first part and then invert the last part. So first part, and then invert the last part. Is there a multiplication on that? Let me see. Yes, there it is. Like that. And then plus invert the first. It'd be better if they put first and last on here. So you had your first part and your last part. Because x and y here is not necessarily the same as the x and y here. It's just a form. And then this becomes invert the first part and then the last part. So x, y prime, invert it, and then the last part. Still isn't what they did there. How can think about that one. Hmm. Well, don't worry about that example because I'm not really sure myself where they're getting this from. Unless that's the last part of the XOR. Let me see. First part flips to that. That's what we just said right there. Well, so let's try simplifying. Okay, De Morgan's right here says if you got two things multiplied together and then a prime on it, it's this right here. You invert each one and put a plus between them. So it'd be x plus y prime. Okay. And over here, oops, that's kind of same deal here. We're going to invert each one of these and put a plus between them. So x prime plus y, and then x prime y. Postulate 4a, the distributive property. Basically, it's just like algebra. You can multiply those together. So we're going to have this times this and this times this. So we're going to have x y prime x plus x y prime plus, and then I'll take this and multiply it times each one of these. So I'm going to have x prime y x prime plus x prime y y. Now I can rearrange these so the x's are together. X y prime, x y prime, and here x prime y, and over here those are already together. Okay, if they're the same, I think I got a property for that. If they're the same, exactly the same, that says theorem 1b says x and x times x is equal to x. Which means this is x y prime, this is x y, x y prime. This is x prime y, and this is x prime y. Just double check everything. Okay, appears to be right. Now I got two things with a plus between them that look the same here, and actually here too. So let's see if I have something about that, like x plus x. Theorem 1a says x plus x or x is equal to x, which means since this is the same as this, there's a plus or an or between them. That just gives me one of them. And same thing here. I don't get the same thing as them though. It's not real comforting. Okay, so x and y. They both need an inverter. Okay, so then facing south. This one facing south. There we go. Okay, so have this go all the way down to two AND gates. And that's going to be going into an XOR gate. And that's going to go to our output. Okay, so our first one is coming from X and not Y. So X and not Y. Our second one is coming from not X and Y. Not X and Y. Okay. And my claim is that I'm correct, which I'm probably not. But sometimes, I remember from past semesters, the book just has some typos. If I can select them all at once and change their direction. Okay, I can. And this is X. This is Y. Okay, so then I claim that it's X. Okay, there's a plus here. So it's my OR gate at the end. And I got two AND gates coming into it. Class. Okay, what's this first AND gate? I got X and not Y. X, not Y. There we go. Second one I claim is not X and Y. Not X. And what did I say? Y. Then I'm going to have that come to an output. And right from the very beginning, I see I'm wrong. Because 0, 0 is given at 0 here. But my 0, 0 gives me 1. So what in the world did I do wrong? Let's see. So this was the XOR gate. X, Y prime, X, Y prime, X prime, Y. Okay. First is same, second's primed. First one's primed, second one just comes down. This I could rewrite in this manner, X plus Y prime. This I rewrite as X prime plus Y. XY prime. X prime Y. X prime Y. Hmm. Assuming I looked at definition correct on that. This says if you have your first item, XOR your last item, first item carries down, you invert to second item. Put a plus between them, invert first item, second item carries down. Um, that looks right. And in Morgan's law, you got two things multiplied together and primed. Two things multiplied together, primed. You take the prime of each one of them, put a plus between them. Did I do that? Prime, prime, plus between them. Prime, primed, plus between them. XOR here, two ands. XOR, two ands, X and not Y. X, not Y. This one is not X and Y, not X and Y. Oops. I better plug myself in. Well, I'm not seeing it. Assuming I looked at the right one. Exclusive OR. Let's look at symbols again. First carries down, prime the second one. Prime the first one, second one carries down. So that says that is prime the second one. Prime the first one, second one carries down. I don't know. Do you just see anything wrong with that? I believe it's wrong because Logic Sim's telling me it's wrong. But I sure don't see any. Assuming this is correct, which I think I saw that in two places. I got about 3 minutes. Let me go back there see if it jumps out at me. Otherwise, we'll abandon that one. No, I just don't see it since they haven't introduced this symbol at all. They say it's xy plus x prime y prime. If I got time. Then xy. And x prime y prime. Okay, now I'm totally confused. It's given 1 also, same as mine. So this is what I think it should be. But this says 0, 0 should be 0. Which means we're both wrong. assuming I designed the circuit correctly here. X and Y, come into those. Not X, not Y. That would match theirs. For this, it's pretty obvious. You got an XOR. So here's an XOR. You got 2 of these coming in. This one's X, not Y. X, not Y. The other one's X, not X, Y, not X, not X, Y. Well, I'll go ahead and stop there. Mine is wrong, but theirs is wrong too. Because if they say that this is equivalent to this, if I design both of these in a circuit, they both should give me the same outputs. Does that make sense?
Yeah.
So I don't know what they're doing here, but it's wrong. So, oh well, we won't waste any more time on that. Next time we'll continue on and practice exercise 1.5.